All right, I'll just get started as people finish filing in. So it's my pleasure to introduce Jennifer Sokoloski as our colloquium speaker, or better known as Jeno to a lot of people. Jeno got her bachelor in physics at MIT and did graduate studies at Princeton and UC Berkeley, where she got a PhD in physics. And I guess you're actually kind of my academic older sister.
Yeah.
So
A lot older.
oh, don't say that. So she was an NSF fellow at the CFA before becoming a research scientist at Columbia. And since then, she's had a number of positions, including president of the American Association of Variable Star Observers, and most recently, director for science at the LSST Discovery Alliance. Jeno's best known for her work on accreting white dwarfs and Novae, which, if you haven't been following along, has actually had kind of a renaissance in the last decade or so, which has been really exciting to see. So it was one of our big motivations for inviting Jeno here today. So please take it away.
Thanks, Tony. Thanks a lot. So as Tony said, in the past decade or so, a little more than the past decade, two facilities that are have come online that are very relevant to the field of NOVA studies. The Fermi Gamma Ray Space Telescope and the Jansky VLA. In addition, or along with the increasing accessibility of, or availability of optical monitoring, these two facilities have led to really a revolution in our understanding of how nova eruptions work. So today I'm going to tell you that story. Then at the end of my talk, the last quarter or third of the talk, I'm going to switch gears a bit and address the question of what our community should be doing and is doing to prepare everyone, all astronomers, to be able to make similar or even more impactful advances with the complex, copious, and high velocity data from LSST. And I should say that some of the stuff I'm going to talk about today on Novae was recently summarized in a very nice review led by Laura Chomik. So if you're interested in anything that I mentioned, you want more details, that's a great place to start. Also, much of the work that I'll talk about, some of it I was not involved in, some I was, and a lot was done in the context of what we call the eNova collaboration, because before the Jansky VLA was renamed the Jansky VLA, when it had just started, it was the expanded VLA. We got very excited about it and started working with it. So we are the eNova team. Okay, so since most of you don't work on Novae, I thought I'd start by motivating why should you at least spend 1 hour thinking about Novae. Couple of reasons. First, Novae are the most common major stellar eruptions. They're all happening all around us. They're very frequent. They're very close. In terms of physics, because they're very close and they're very frequent, it gives us a nice opportunity to observe some phenomenology that's very, oh, I just realized I didn't take my mask off, sorry. To observe some phenomenology that's very common among stellar transients and systems that host transients, and also anything that accretes. So accretion inflows and outflows, surface, nuclear burning on the surface of an object, shocks, particle acceleration, and dust production are just some of the ones I'm interested in. There's other physics as well, but those are of particular interest to me. Also, if anyone's interested in type 1a supernovae or supernova cosmology, novae are actually the main barrier for some accreting white dwarfs, actually many, that would otherwise end up exploding as type 1as. So if you want to do population synthesis and understand the progenitors of type 1as, you have to, or at least someone whose modeling you trust has to know something about Novae. Okay, so just to go through those 3 points briefly, in terms of frequency and proximity, here are two plots from a nice recent paper by Kishilet D. using the Palomar-Gattini IR Pathfinder IR survey, which detected quite a few novae. So on the left is just a plot of showing in the galaxy, the galactic plane, his work, and 2 prior surveys, just to get a sense of how novae are distributed and the numbers. So these are 3 papers, I think, 2016, 2018, and you can see quite a few novae are detected. The Gattini ones are the stars. I was marginally involved in that, but Keisha really led all that. On the right is a distribution of possible galactic nova rates from their simulations and the fraction of simulations that would give the number that they actually ended up observing. And I'm showing that you don't need to worry about the distribution, but just so that you can appreciate that the peak of that distribution is a little lower than 50 novae per year in our galaxy. There are 52 weeks in a year, so I think of novae as about 1 per week. So if you're used to thinking about supernovae, if you think about transients at all, and it's like 1 per 100 years in a galaxy, you can think of novae as more like sort of popcorn to the big event. They're happening all the time, and then every 100 years you get a supernova. So shifting a little bit to some of the physics that I mentioned, accretion inflows and outflows. Just 2 examples that I'm particularly interested in and was involved in some time ago. This is on the left, an accreting white dwarf called R Aquarii that accretes from a red giant donor star. These are my favorite kind of accreting white dwarfs. They have much less well understood disks than those in cataclysmic variables, where a white dwarf accretes from a nearby tight white dwarf main sequence star. What's shown there is a jet. So if you didn't know that white dwarfs can produce very dramatic jets, this is a Chandra image of a jet from that accreting white dwarf. And it's a little aside, it's not about novae, but I find it very interesting that cataclysmic variables, where you have accreting white dwarfs with small disks, they don't produce jets like this. The main difference between this object and a cataclysmic variable is that it has a larger accretion disk. And somehow, which we don't, as far as I'm aware, still understand, that disk affects what is happening near the white dwarf itself, which is producing this very dramatic and changing jet that we see doing all kinds of fun things, like sometimes switching sides and doing all kinds of things. Anyway, on the right is an image of an accreting white dwarf binary that actually did erupt 2 years before this image was taken. And I'll be talking about this particular system a little bit more. Here, I just wanted to show you a little bit about one of the nice things about novae is they evolve on very convenient timescales for you to see some of the interesting structure. So typically for the early shocks, those evolve on timescales of days to months, and you can really follow those. This image is at 2 years, taken with Hubble. The red is H alpha. The yellow is forbidden oxygen 3, probing a denser sort of column of material across the front because it's an edge-on binary. Some other stuff, but you can see a lot of structure. So really my point there is just that look at what we can see. Okay, final point as novae as barriers to type 1a supernovae. The real question is how much material is accreted onto the white dwarf and how much is expelled as after a certain amount of time that accreted material reaches the conditions of pressure and temperature that are sufficient to trigger a nova eruption. And if you integrate over time, which one wins, or how does that evolve? And it's actually a pretty tricky question in terms of how much a white dwarf accretes. The challenge is that there's practically no system where that accretion is constant. There are disk instabilities, there's high states of the donor, there's various things that contribute. So unless you can monitor perfectly, continuous coverage, it's very hard to get a sense of how much is actually being dumped onto the white dwarf. On the other side, for the novae, we can find them. We know when they're happening, but it's very challenging to actually do a good estimate of how much is expelled. I won't go into all those reasons. I just threw a few things up there as an examples. The ejecta are clumpy, which means that like if you're using radio emission to try to get a sense of how much mass there is, you have to guess how clumpy they are. There's the overall density structure even beyond clumps. And anything you do is dependent on some model. And those often change. So it's still a bit tricky to even figure out for a particular accreting white dwarf, is the white dwarf growing in mass? For many systems, individual systems that have been studied, the answer is we don't know. So, but my goal is that the more we know about Novae, at least we can address one side of this equation. Okay, so now you're motivated. I'm going to switch to my story. It starts with gamma rays. So in 2008, NASA launched the Fermi Gamma Ray Space Telescope. And 2 years after that, in 2010, gamma rays were discovered from a nova. Now, that first one, which is, I just realized I have my stick, V407 SIG, which is shown here, was very exciting. There were science papers written about it. But that's a very special or unusual kind of nova in which the white dwarf erupts into the wind of a red giant donor star. So accreting white dwarfs can accrete, as I mentioned earlier, from either a red giant, well, all kinds of things, but the ones that produce novae are typically accreting from either a red giant or a main sequence star in a type binary. So this one was accreting from a red giant. And so the explanation that the community came up with, the authors of this paper, with which I was included and totally bought in, the only reason we saw gamma rays, we thought, was because the ejecta were plowing into the wind of this red giant. That can give you strong shocks and accelerate particles and produce the gamma rays. So we thought we won't see very many novae producing gamma rays. Okay, then I think 2012, another one was detected, V959 Mon, and since that time, at least 20 novae have been detected in the gamma rays. These are clearly a category of gamma ray transients. Here's just some images for fun. And on the right, some gamma ray light curves. The x-axis there is a little over a month, so 0 to 40 days. And the y-axis is gamma ray flux. And so the main thing, this is just a sampling of light curves taken from the nice review I mentioned earlier, led by Laura Chomick. And what I want you to take away from this is really that the gamma rays wiggle around a bit, typically for about a month. Yeah. Sorry, what about them? Yeah, well, are they from different? No, they're from also Fermi. So I guess I don't remember exactly what sets the sensitivity. Of course, it's scanning all the time. So some of their pointings are more sensitive than others. And also, as you can see, the underlying gamma ray emission from these sources is wiggling around. So some of those, it probably did drop. And some of those, just the pointing wasn't particularly sensitive. Feel free to ask me questions, more questions as you go. Okay, so this discovery of gamma rays from novae was a big surprise. The main reason was because I've outlined here, gamma ray emission, this is GeV gamma rays. And what was detected from novae is a continuum emission, not line emission. So it's still detected. Okay, so to produce this kind of gamma ray emission, what's almost certainly required is a population of relativistic particles. Okay. How can you get such a population? A very natural way in a stellar transient is diffusive shock acceleration, diffusive acceleration of particles as they bounce in front of the shock and get re-accelerated every time they cross the shock, and that happens repeatedly until they get accelerated to relativistic speeds. But the energetics seemed incomprehensible. So the detected gamma ray luminosities from novae are about 10 to the 35 ergs per second. Okay, but much of the emission that's, let's think it through, a lot of the shock power does not go into accelerating particles. Just a small, say a few percent at most, goes into accelerating particles. Once the particles are traveling at relativistic speeds, then only a small fraction of that, those produce gamma rays in the Fermi-Lat band. So working through those efficiencies, the shock power to produce the observed gamma rays seems like it would need to be about 10 to the 38 ergs per second, typically in Novae. Okay, for a accreting white dwarf, for a white dwarf, that's Eddington. That's the Eddington limit. So it's telling us that these shocks that we never knew about seem to exist and seem to be as powerful as any other aspect of the nova. Okay, so this was surprising, again, as I just said, because first of all, the flow speeds in novae are non-relativistic, so we don't expect a lot of relativistic particles, or we didn't. The ejecta, a lot of the phenomenology of novae works reasonably well if you assume that novae just, when the material on the surface of the white dwarf ignites, that material gets expelled, that it's roughly a spherical ejecta of 10 to the 4K thermal material that has what we borrow some terminology from cosmology, call it a Hubble flow with the velocity proportional to radius. Just, you don't expect a lot of strong shocks in a situation like that. And past papers on expected gamma rays predict line emission in the MEV range, not continuum emission in the GeV range. So this was all a big surprise. So that raised the question of powerful shocks in novae. Is it possible that these very well-studied events are hiding powerful shocks, and they somehow have been for all this time? So we know that this subcategory of novae, that where the white dwarf erupts into the wind of a red giant donor star, which we refer to as embedded novae, some of those have powerful shocks. So an example that I like, because I worked on it a lot, and it's also very exciting anyway, is RSOF. And this is from showing some X-ray spectra from a prior eruption in 2006, where this is taken with the Rossi XTE, which is now defunct, an old X-ray satellite. And what this shows is how first of all, the emission here is 5 to 20 keV, so it's a little harder than like Chandra and current X-ray instruments other than NuSTAR. What you see is that the X-ray spectrum evolved quickly, like over just 2 weeks. And this was exciting at the time because that evolution was exactly what you'd expect from a, like if you had a supernova sped up and you're set off Taylor phase for the blast wave. So we had like a mini supernova blast wave moving into the red giant wind. And that was one of the things we achieved from that, or we attempted to do, was to actually then get a sense of the mass of the ejecta by when it started decelerating. So again, though, very model dependent, but our work there suggested that it was very light and that white dwarf was therefore very massive, because it has to be massive to get an ignition with very little fuel, and it might be a type 1a progenitor someday. Okay, so we know that there can be powerful shocks in novae if the ejecta move into a wind, because we see them, that's the collision between the ejecta and the external medium. But what about other novae? There's no reason prior to the gamma ray detections for us to think so. The shocks in normal novae, well, we know that it has been known for a long time that they produce X-ray emission. That's a little harder than you would expect from the nuclear burning on the white dwarf surface. So just a few keV. And so that has to be from shocks, but that X-ray emission was typically quite weak. So shocks were thought of, like in this context, maybe 10 to the 33 or 10 to the 34 ergs per second, closer to actually 10 to the 32 in some cases. So they were thought of as sort of like in the bells and whistles category, not as one of the most energetic parts of the system. So that's my first bullet there. The second, even once gamma rays had been detected from classical novae, the normal kind with a main sequence donor. And we went and tried to find the powerful shocks from their X-rays behind the shock heated gas. And some work led by Sokoloski was actually able to use NuSTAR to get an X-ray detection of one system while it was gamma ray bright. So you can't argue, okay, we missed it, it used to be bright or whatever. And also you can get a good measure, he was able to get a good measure of the column density, so you can do a pretty good job of correcting for that. Still, the X-rays were orders of magnitude too faint, 2 orders of magnitude fainter than what theorists would have predicted for a powerful 10 to the 38 ergs per second shock. And this issue is not resolved. That's one of the main open questions that I'm interested in for Novae right now, is how is it that we're not seeing evidence other than gamma rays for these powerful shocks? Maybe they're not radiative, even though the theorists say they have to be radiative shocks to be able to generate the gamma rays and various things, but just leave it for now that it's still not clear why we're not seeing other evidence for the shocks. Okay, so moving on to the gamma ray production itself. I've already argued that you need to have relativistic particles, but let's say you do, then how do you get gamma rays? So 2 mechanisms that have been discussed are what are referred to as the leptonic and the hadronic scenarios. So leptonic is basically inverse Compton scattering, and hadronic is if you have relativistic protons that collide with other protons that are effectively at rest, even though for us at rest might be moving at 1,000 kilometers per second, but compared to the relativistic protons that are at rest, those produce neutral pions. So the red things there are my proton cartoons, and then the blue things are the neutral pions that then decay into gamma rays. That's another scenario. Now, a theorist, Brian Metzger at Columbia, has led a lot of papers on since this exciting discovery of gamma rays from Novae. And so he has suggested that because the environments of these shocks are very dense in Novae compared to other situations in astrophysics, that these shocks act as calorimeters in the sense that every relativistic proton will collide with another proton. It can't escape because it's a very high density material in the ejecta. So we can really, the gamma rays that we're seeing really are is measuring the power of the shock. We're not missing a lot of them. So they're probably not producing a lot of cosmic rays. Okay, final slide on the gamma ray discoveries. Just to summarize Novae's gamma ray transients. They are ubiquitous. So in fact, the majority of novae, if they're close enough to us, have been detected with Fermi. Close as a few kiloparsecs. So 3, I think all, or not all, the majority within 3 kiloparsecs, but even out now to 5 kiloparsecs are detected, but not all. So majority, but not all. There are some that are nearby that are not gamma ray sources. So it's common, but there must be some combination of parameters in a nova that leads to us not seeing gamma ray emission. The gamma ray emission is fairly similar in terms of the spectra of these sources, the timing. If you just say, well, if you count wiggling around is the same thing, they wiggle around for about a month. But there are also differences. The intrinsic luminosity varies by a factor of 2. They're not gamma ray standard candles at all. But they're also, it's very robust, this production of gamma rays. You don't need to fine tune parameters to get it. So we see gamma ray production in novae with a variety of speed classes, which is one of the main parameters, one of the main variables for novae, and also whether they're embedded in the wind of a red giant or not. Both types produce gamma rays. So for novae, it must be easy somehow.
I was wondering what function of the X-ray detected novae out of this subset of gamma ray detectors?
So I'm thinking because that probably depends more on which ones have been observed rather than how many had intrinsic. Like basically for nova, if we point at it with a sensitive instrument and it's within 5 kiloparsecs, it will be detected. But some, our proposals didn't get accepted, or we were working on another one, or not all were observed, or some other team used a different facility at the wrong time, or I shouldn't say wrong. Some people are very interested in the persistent burning on the surface of the white dwarf, which produces very soft X-ray emission, and they observe later. I am more interested in the shocks, and I like what's happening early, but some other teams look later. So I don't know, I'm sorry. But I think most of them do have some X-rays. Okay, so now I want to move on to the radio, the Jansky VLA. This is obviously not me or anyone on my team. Is Jodie Foster pretending to use the VLA. So we did actually use the VLA. It's still great though that she's there as a spokesperson for this facility. So in, I guess, the decade leading up to 2011, the VLA, the 1970s era electronics were replaced with modern electronics, and that improved its sensitivity by like 3 orders of magnitude. So it was practically like a new instrument, which was amazing. So my group started, the ENOVA collaboration started because of this new expansion, and we started looking at a few novae. So here is just one sort of otherwise normal and not extraordinary nova. It was actually a little far away, 6 or 7 kiloparsecs, and we did some radio monitoring, which it was difficult to do previously at this level because it took so much longer to get one good high signal noise measurement, and you couldn't get measurements down at these low flux densities before the Jansky VLA expansion. So what we saw is what's shown there, and I'll explain a little what that is. Those dashed colored lines are what you would expect. Oh, and this plot is days after, the x-axis is days after outburst for about 3 years. So it's like 3 years of monitoring, and the y-axis is flux density of millijanskys. So the dashed lines are what you would expect from an expanding ball of 10 to the 4K gas. So basically, it's expanding at constant velocity. So the flux density goes up as just the area. So, R squared of the thing you're looking at, or time squared since it's expanding at a constant velocity. And then eventually the outer parts start to become optically thin at the highest frequencies first. So the highest frequencies turn over first, and then it shrinks. And once it's all optically thin, the spectrum is flat and they all fade at the same time. So that's what you get with the dashed lines. So this is what we saw, and you can see that there's a big deviation from those dashed lines at the early times. That early radio flare brightened too fast to be any expanding thermal structure. So that was confusing for us. Of course, because we can measure the velocity with optical spectroscopy. So we know how fast the flows are. So that was brightening too fast, or even if you don't know that, if you know when the thing started, it shouldn't brighten faster than time squared. So then it's like, what's it doing? It's brightening too fast. And the spectrum was very strange. There were all kinds of peculiarities. So in this paper led by Miriam Krauss in 2011, we published a paper in the AppJ issue that was dedicated to the first papers from Jansky VLA, and said something weird is happening. It looks like it might be non-thermal, but we don't really know. Now, at that time, the first gamma ray discovery had already happened, but because it was this kind where we thought it only produced gamma rays because it was an embedded nova, and this is a regular nova, we didn't make the connection. We just thought there's some early flare, and we don't know what that is. Okay, so from a review by Laura Chomik, here's a couple of examples. more recent examples. So the top row are actually optical light curves. So again, the scale, the x-axis is the same, about 3 years of monitoring for each of these. And yes, I did handpick the ones that look the nicest from the whole set. But the top row is optical light curves, and the bottom is the radio in a similar style with the different colors for different frequencies. And what you can see from the bottom panel is that other novae also had some early time radio flares. And here it's smaller. It's preferentially, it's more pronounced at low frequencies. And here there's kind of like a bump. It's less pronounced, but this is just to give you a sense of the different way these things can look. But what we found is that it's actually fairly common for the radio emission to have some flare before the thermal evolution, the evolution that is modeled reasonably well by that expanding 10 to the 4K ball. Of course, now, by the time we were had collected data on more novae, we also Fermi had revealed that many regular novae produce gamma rays. So now it was becoming more and more clear that this signature of non-thermal emission was likely synchrotron emission. And although it doesn't explain directly what's going on with the gamma rays, at least it's another signature of relativistic particles. So we now see in the radio, in addition to the gamma rays, that there's a lot of relativistic particles in the radio producing synchrotron emission. If you're actually curious about in the top plot what's happening, you might, or if you're thinking, you might have noticed that there's some dips here. Not all the optical light curves have that. I'll get back to that. I might touch on that briefly later, but I'll just give you the answer. What I think the answer is that that's dust. Those are dust dips. And for novae, for a long time, they have been seen to produce dust, and that produces these optical dips. But it was an open question: how can you have dust being produced in such a hostile environment with a lot of UV emission and X-rays and a lot of things? But thinking about shocks actually led a team at Columbia. Andrea Derdzinski was the lead of that, to suggest that behind the shocks, like what I think is seen as supernovae, you can get, because of the increase in density, you can actually get into a situation where you have some increased cooling and then increase in density and get some catastrophic cooling, which produces an environment that is suitable for dust formation. And so it could be that the dust formation is related to the same shocks that are producing the gamma rays, or I should say the same shock system, because there's actually a forward and a reverse shock. In fact, one of my last, most recent PhD student did look at the time relationship between the gamma ray production and the dust production, and it's consistent with that idea. Okay, so beyond radio light curves, we were able to use the VLA in combination with VLBI facility to get some imaging. And so here's shown here on the left is an image of this Novae. Showed you a light curve of recently, a while back, and you can see that the red, yellow, this colored emission, that's the image from the VLA, and that's tracing thermal emission. You can see that it's extended in the east-west direction, which is horizontal here. These black contours are actually from a VLBI facility. Those trace low frequency emission in the radio, and they actually trace synchrotron emission because of the different spectrum of the thermal versus synchrotron and the sensitivity of the different types of facilities. These trace synchrotron emission. So what we learned here, I'll tell you, in a little while later, so this was a few months into the eruption, a year or two after, what we saw is that this structure expanded, this east-west structure faded and revealed that there was a dense structure here in the north-south direction. This is a binary that is, we're looking at edge on. So if you're the, you're the observer, so this is the equatorial plane here. And this is the sort of polar directions. So what we learn from this observation is that the synchrotron emission, which is presumably tracing the shocks, is happening if you imagine that there's a torus in the equatorial plane, right where the other flow, the more polar flow, hits that torus. So that was a big aha moment. If you're having trouble seeing it here, you can look at this cow, because our previous model was the spherical cow. This was created by Jennifer Weston, my past graduate student. Imagine that at the early stages of the nova eruption, a torus, a slow torus is produced in the equatorial plane. And then later there's a wind from the still burning white dwarf, and that wind collides with that torus. And then you get like this cow with a very tight belt and shocks where the wind is hitting that equatorial torus. Yeah.
The fact that the left is there, the right is just distance.
I don't know. It might not be. It might be slightly different. But like, I don't even notice that, because that, to me, like, there's so many things that are often like not exactly symmetric, and like little bumps here and wiggles there. Like, it looks, I don't know the answer to that, but I don't think it's I don't know if it's important. But I could point out also that you notice, like I'm talking about the region where there's a collision between a spherical flow or some wind or polar structure and an equatorial, a torus. You notice that we only see the synchrotron shocks there, not like there, if it was like some kind of X or all along. We don't understand why. Also, if you're eagle-eyed, you might spot there's some shocks there, which might have to do with some collision at an outer region. So it's not quite as simple as I'm gonna sort of, the story I'm gonna tell is simpler than the reality probably is. There's probably more than one simple shock region, but it seems like the dominant shock region is probably where the spherical flow or polar flow hits the torus. Okay, so here's the picture, as this is from, again, Laura's review with Brian and Ken Shen. And the picture is here. You have the binary, it's rotating, initially produces a torus or some material in the equatorial plane. And then at later times, you have a wind that hits it, that sets up a forward shock and then a reverse shock. And one of those shocks, or both of them, we don't actually know, accelerates the particles that then produce the gamma rays. And the late time structure looks like this. Now this picture is actually something I just grabbed from a gamma ray burst illustration, but I like the fact that it actually perfectly matches the way we're envisioning the evolution of the nova eruption.
You know that the torus isn't long-lived?
It is. It is long-lived, and we see it at late times. That seems to dominate the thermal radio emission. So in fact, I think most of what we've been observing at late times in the radio and doing mass ejecta estimates is just the torus. Okay, so additional support for this picture, there's some theoretical work by Ken Shen and Elliot Quatert that does suggest that when the white dwarf photosphere expands after the ignition, that it is actually what you would expect for a flow to be generated out of the back of side of the donor star, the L2 point. So that provides some theoretical underpinning for this torus being the first thing that's expelled from the nova. There are also plenty of observations. Some are old. You see here, I've listed some papers, some way, way back, providing evidence for rings. in novae. And it's just that I think the community generally thought they were less important than we know. Like, yeah, you have a spherical thing and it might have a waist or a belt. And now there's a shift more towards thinking that's actually the dominant structure. But there's been evidence, like, if you do look for optical spectroscopy in old Hubble imaging and old Nova shells, they've been seen before. Okay, so I have a whole section next. So this is that we didn't then just say, okay, we're done. This actually, all this finding set up a race among people in the Nova community to see now what can we solve now that we have a new picture for how novae work. These are actually kids in New York running, but it was a race of researchers. So I have a section here, but I want to be sure to, I've been very slow for some reason in my discussion with you guys. You're very friendly. So I have a section I'm going to buzz through so I can say at least something about LSST, which I want to get in. So this is with this new understanding of how novae work, then the community tried to address some problems, some longstanding problems, and also see then what can we learn if there are these powerful shocks. Here's some plots from a paper led by LSST, who this top is an optical, phenomenal optical light curve from the bright satellite of a nova, whose name I forgot to write down, and I forgot. Oh, here, B96 car. And here's a gamma ray light curve on the bottom. Now, what we found is that the flares were correlated. And in fact, the gamma ray flares lead the optical by a few hours or even less than an hour. That's only possible. That measurement was only possible because of this satellite, very high cadence monitoring. So the conclusion that we drew from that is that mostly that Elias theorists who are working on this drew from that is that it's the shocks that are actually powering the optical emission, in this case for the flares, and maybe in general more for novae than was previously appreciated. If you ever look at a gallery of nova light curves, some of them are very smooth and they look like they should be in a textbook, but some of them have crazy flares and wiggles, and you start to think like, oh my God, so much is going on, we'll never understand it. But perhaps really what it's about is just the energetics of these shocks. Like maybe there's some sputtering in the flows that are leading to those shocks, and that's propagating all the way into the optical light curves. As I already mentioned, so maybe I'll skip this. It does seem that there's a connection between the shocks and production of dust. Oh, I'll say one more thing here because I like this one. In one nova, RSO, which is one of my favorites, we, working under the leadership of Yanko Nikolov, did some optical polarimetry and saw, so that's a system that has like the direction of the polar flow and the orbital plane is known. And we saw polarimetry suggesting dust production along the sort of polar axis very early on, and then dust in the orbital plane. So that was the first time I'm aware of that. Like, so in terms of timing, it looks like the dust production is associated with the gamma ray producing shocks. But this time for this system RSO, it seemed like we could also connect them in space, that they seem to be aligned, that dust was being produced in the torus or in the orbital plane. That was kind of cool. Okay, final thing before I go on to the LSST stuff. Again, RSO, greatest stuff ever. Erupted in 2021. And this is an embedded nova, erupts into the wind of a red giant, and it was detected in the TeV range. So not only did it produce GeV emission, but TeV emission from what's previously was thought, these kind of wimpy little novae, they're 1,000 kilometers per second, they're all over the place. Now they're producing TeV emission. Of particular note was that, let's see, one of these curves is, the blue is the GeV emission detected with Fermi, and the red is the TeV detected with Hess, and they are offset. So currently there's a debate in the community about whether that means whether one is associated with, say, the shocks in the torus and the other with the shocks as the ejecta collide with the wind, or whether it's reflecting the different time scales, the amount of time it takes to accelerate particles to a higher energy. So you have to go back and forth across the shock more time. So maybe that's why the high energy flux is delayed compared to the DEV flux. So when I started working on Novae, I never thought that I would be getting into the TeV range or thinking about particle acceleration timescales, but now we can do that. Oh, and there's another source called T-Corbor. You've probably never heard of it because you don't work on Novae, but it's less than a kiloparsec away, and it's one of these embedded Novae, and it erupts every 80 years, roughly, plus or minus, but it's due in the next few years. And so if it erupts, it's going to be, you'll probably hear about it, even if you don't work on Novae, because I'm guessing it'll be TeVs and TeVs, so it'll be very exciting. Okay, I'm going to skip over this last part so that I can get to at least little about the Rubin Observatory. There's Vera Rubin. Okay, you probably know the basic stats of Rubin, and I heard that Melissa Graham was here not long ago and gave you a colloquium, so I'll just go quickly over it. You know that it's a big facility, and it's going to observe tens of billions of stars and galaxies and produce a lot of data, 20 terabytes per night, and of interest to me and people who work on transients, 10 million alerts per night. So that's a velocity that is challenging to deal with. So you probably know the stats. Also, the cool thing, one thing about LSST, the mirror, it's got this large, unusual structure, so you can compare it to other facilities, and this very large field of view. It has its main science goals: dark matter and dark energy, cataloging the solar system, exploring the changing sky, and Milky Way structure and formation. Here I will pause, though, to go over some of these dates because they're relevant. In a few months, the camera will be shipped from SLAC to Chile to begin the final integration of the various components. The dome is expected to be complete a few months after that. They might, the construction team put the commissioning camera on Sky. After COVID, there were some delays and they thought they'd just do commissioning with the full camera, but now there's some counteracting delays and they might actually put it back on. Then there's the final telescope mount assembly. That's the TMA. The camera will be installed. First on-sky photon through the camera is expected in about a year. So the full system for first light is now expected in January 2025. So that's just over a year from now. Okay. Obviously, after first light, there's commissioning, and then they start the survey. And if you don't care about transients, then you have to wait a while till you get the data release. However, I want to argue that you should still pay attention to the fact that first light is just over a year away. So for example, if like me, you tend to think in terms of NSF proposals, should I write my NSF proposal on LSST this November? I am going to. I don't know if you're going to. Also, the director, Željko Ivezic, has decided that along with first light, they plan to release a small sort of like teaser data set, sort of like a first light data set. And he says small example data set, but I don't know exactly what that means. And so it would be cool to be able to write a paper from the first data, and like it's going to be LSST data. So I imagine there will be a lot of science in it. And so that's just a little over a year away. So that's sort of the beginning of what we think of as like early science with LSST in just over a year. And then they do commissioning, where science quality data will be available from commissioning. For some members of the community as well, if they're want to join a commissioning team, the official start date is in late 2025. So that's about 2 years away, but there will be these previews beforehand, and that's when there will be alerts flowing. So if you're interested in transients, you definitely want to have your ducks in a row by that time. Okay, so it's going to produce a lot of data. Okay, so now I just want to for the last 5 minutes, talk a little bit about community preparations. And my picture here is so that the first year of data doesn't slip through our fingers. So there's several things that the community as a whole, I'll just wave my hands and say the community is doing to get ready for LSST. The LSST science collaborations actually formed, I think, back when those facilities I was talking about, like in 2008, and helped write the science book and helped get really the project funded and started. So anyone who has data rights, anyone at a US institution can in principle join a science collaboration. These are just groups of individual researchers. They're generally not funded. So there's a variety, except for dark energy, which gets some funding from desks. So the level of activity depends very much on just the people who are involved and how busy they are. I'm part of TVS, Transients and Variable Stars. They're super organized and super active. They're doing all kinds of stuff. But some of the others, I've heard a colleague of mine put in the application to join and like it went into a black hole and she never heard back. So it's not clear that these all are active, which is understandable because everybody gets busy and they're not really funded, just people getting ready. They're community alert brokers, which you might have heard about, with 10 million alerts per night. It's difficult to make sense of that. So the construction project has decided that I think 7 teams will have access to the full alert stream, and then they'll provide some kind of brokering service. So those different brokers will have different science focuses and maybe different technical ways of feeding or sifting through those alerts for the community. Anyone can see those proposals went, I think, in 2019, and they've selected 7 and then 2 downstream brokers. Oh yeah, different capabilities in science focuses.
Kind of rationale for choking it off. Like I understand that like that's too much for most people, but if someone wanted to, why is it just like a data issue?
Yeah, I think it is. I think they like literally they just can only feed the full stream. They only to so many a finite number of groups, and so that's the way they tried to do it. Yeah, but it's technical, not philosophical. Okay, so now is the organization that I have been actually for the past 5 years very involved in. I took a partial leave 5 years ago from Columbia Research to actually try to think carefully about what does the community need to get ready for LSST. So first let me just say what LSST Discovery Alliance is. You might have heard of LSST Corporation. So that's the same thing. We changed our name. Now we're Discovery Alliance. The corporation was originally to get LSST started. So LSST Corporation solicited and received the first private funding that helped get LSST going. But now we're focused on working together to figure out what is needed to help astronomers really make the most of LSST. Now I say we, this is just a consortium of institutions, mostly universities, but like a museum or 2, 1 foundation, but mostly universities. And it's also not static. So I again say we, but like Columbia, my institution was in it for a while and then was out and then was back in. Different organizations, every year there are a few that leave and a few new ones that join, and it is open to anyone. Here's my little pitch part. Anyone can, any institution that is really interested in getting a lot out of LSST can join this collaboration, this consortium. Okay, so we try to come up with programs that are the kind of things that an individual institution and certainly an individual PI could not run themselves. Since we're trying to harness the power of 30 institutions, we want to think what would the community need, and we fund them with private money. So one thing I've been doing is pitching ideas to foundations and private donors to get funding. So in the past couple of years, we did have some success. And we launched 2 multi-million-dollar programs. So one is a new prize fellowship called the LSST DA Catalyst Fellowship. That's funded by the John Templeton Foundation. These are a subset or most of our first 2 cohorts of fellows. These fellows sit at member institutions, so they can choose from member institutions where they want to go. It's cross-disciplinary, and that there are actually a few social scientists involved who are studying the practice of science and how it's changed by the introduction of big data. So it's kind of interesting there. These fellows have structured mentoring and leadership training and cohort building. We try to help them develop a strong network. They have like advisors from the science collaborations and a whole team of advisors. They have automatic access to the data previews. So that was one of the big initiatives we launched. Another thing is called LINK frameworks, where I'll say that LINK is short for the LSST Interdisciplinary Network for Collaboration in Computing. That's an umbrella that all of our programs now fall under and are connected by. So what this is an effort to go beyond what the federal government funded tools will provide. So you heard that actually the timing of my colloquium with respect to Melissa Graham's is perfect because they're providing some tools. Most researchers think they would like additional things beyond those tools. And so that's where we're trying to pick up where they left off. And we partner very closely with the construction project. We have them on our committees and us on their committees, and we work together to try to really pick up where they left off and build on what they're already doing. So this is a project that is, I think, a $15 million project funded by Schmidt Futures Foundation. They're building software with teams of software engineers seated at University of Washington and Carnegie Mellon. And they have some initial focuses. One is photometric redshifts. Let's see, photometric redshifts, moving objects on the sky, and light curves, and are working to, like I said, take what is already being done and go beyond. So for example, for photometric redshifts, oh, sorry, I see that I should be done. I'll be done in a second. The project will have an algorithm that you can use in their Rubin science pipeline. This software will have multiple methods that you can use and compare for different use cases, and a capacity for users in the community to upload their method, their algorithm, or their software so others can compare and decide how they want to use it. Through this, this is all open source, so it's all very open to help the community. And we're running some funded incubators where members of the community who say have their own, they've started to work on some code, but it can't run at scale, or it's too slow, or has some problem, they can apply and go spend some time, or send a graduate student or postdoc to spend some time with these teams of professional software engineers to help them get their code up to snuff for LSST. And then that is also made available to the community. So we select projects that would be of benefit to the individual researcher, but also widely. Then there's some other programs that we've had going for a long time. So for quite a while, you can look those up on our website. As I hope I've conveyed, there are some benefits to membership if you guys are interested, in particular priority access to our programs, and also a voice in shaping those programs. I'll end there. Not the one I'm wearing, the other one. Should we share?
Thank you. All right. Yes, hello. Testing. Yeah, I just asked one quick question of, so, the gamma ray background in our Milky Way, people like discuss whether it's self-interacting dark matter and stuff like that. What's the current picture on how much of this could actually come from a background of white dwarfs? And does this new picture change that at all? Or is this all much higher emission than the gamma rays that could be potentially associated with like self-interacting dark matter? Do you know?
So the real answer is I don't know.
Okay.
But I can just think, even if we had 50 novae per year in the galaxy, most of those, other than like maybe 10, or we wouldn't detect even a background signal from. I don't think that this would be relevant for that. That's my gut feeling.
Okay. Anna, did you have a question? It's already on.
Okay. So I have two questions. One on the Novae. So I was curious about the dust production, and you mentioned that in one case you saw it kind of spatially segregated, and then it's a function of time. So just wondering, like, how much of it does get destroyed? Like, do you see like levels kind of dropping off, and then like and how much actually survives?
I think a lot of it does get destroyed, because once it's created, but then it expands, and it is still a hostile environment for the dust. So I don't know what fraction actually survives, but like when you see the light curve dip and recover.
Oh, I see.
Yeah. So
I see. That's exactly what happens. I see. Yeah. So I guess it wouldn't then be maybe a significant source of dust in the universe.
I don't think so.
And my second question was about like the teaser data sets for the LSST. It seemed like it worked really well with GWST, and I think part of the nice part was that it served different communities. So is there any discussion or like place you can look up or like suggest like things that we would like to see as a part of the data set?
Oh, that's a really good question. So I think Jelko, the director, is being very non-committal. And because what if something happens and then for some reason they decide not to do that? The current focus of getting community input is a little more on finalizing the observing strategy, and also during commissioning. How, of course, the commissioning team, they have a certain benchmarks that they have to test, but they can do it in different ways that different science communities might like. But that's interesting about the teaser data, because I'm also very interested in that. So there's no formal process that I'm aware of, but I can talk to some people. So I think that one might be a little informal, because they don't want to promise that there even will be a teaser data.
I guess a surprise is fine too.
Yeah.
Pass the Peter.
Yeah, great talk. Very, very cool stuff. I was just kind of curious about this this torus material and like what sort of time, what sort of time scale of mass loss we should think about, how that was ejected and where that's coming from. And maybe is it just material? Is it so close in that it has to be from mass loss associated with the eruption event, or are you probing something from longer term?
So for most novae, I think it has to be from the eruption itself, and so it's probably expelled. So novae have different. I wasn't very concrete about timescales, because some of them happen in like hours to days, and then some take years. Like they have these different speed classes. But it seems that like if I take a typical one, maybe in the first days is when the torus would be days, maybe weeks, expelled out of the back of the donor star, the L2 point.
Yeah, it seems like there's also evidence growing that even normal supernovae, a lot of them are probably in binary systems, and the mass loss might be sculpted in the same way. So there's probably a lot of analogies to other types of transients. Kyle first.
So you mentioned the novae are most commonly powered by white dwarfs accreting from main sequence stars or giants. Is there a reason why like AMCVN aren't contributing significantly? Is it just because they're much more rare systems, or?
So
Yeah.
White dwarfs accreting from white dwarfs.
Yeah.
Right, so those are accreting, they need to accrete hydrogen-rich material to trigger the regular nova, right? So AMCVN is accreting some carbon, but there can be a
There's helium, right?
helium, so there can be helium novae. So I don't know if there's ever been seen a helium nova has been seen, but I don't know if it's if there's one from an AMCVN system, but mostly because these are hydrogen-rich fuel.
Thank you. So going back to the aspherical cow picture, is it right to think of this as sort of, it still seems like you have some dominant large scale asymmetries, maybe with a large large dipolar mode and an equatorial belt. Is that an accurate, like variations on a theme where you still have maybe some spherical symmetry or axis symmetry? Is that an accurate characterization, or is there still is there evidence for other large scale asymmetries, like dimpling, bubbling, plumes in other directions?
Yeah, so the spherical cow is extreme oversimplification. Let me take you back to the HST image of so this is actually the same nova where I showed that radio image, and then I had the cow with the belt to the right, right? So you can see there's more structure there that I ignored, right? So there's a ring, there's these little things here, which I think of in my head as jet knots. And other novae also have other bubbles and plumes that are thin, that are not just these big bipolar lobes. So there is other small structure.
All right, well, Jenna will be around with us all day. If you have more questions, let's thank her one more time.